However, I think what is clear now is we have methods at our disposal to design the PI controller, but they're not perfect. They're far from perfect. We need better methods to design our PI controller. And therefore, luckily, we have a tool which is the Bode characteristic. A Bode plot is something which gives you lots of insight in the system, which is measurable quite easily at the setup, at all setups in practice actually, and at the same time we do not need lots of mathematics to use our Bode plot to design a controller. So this is a general system. We have the input, the torque, we have the output, the position of your rotor, for instance, or the speed. You see that by putting in one certain frequency at the output, you will also have a certain frequency. You will have the same frequency. You use a system, you put in one certain frequency as an input, you will get the same frequency as the output. So you get the sine wave at the same frequency. But it is very logical that your output cannot follow your input. So your output has a lower amplitude than the input. Moreover, if it cannot follow, you also have a sort of delay. And here we have this phase lag between the input and the output. We get a certain phase lag. Well, actually, by doing one such measurement, we do not know much. We need that measurement at every possible frequency. So we need to redo that measurement for different frequencies. For instance, at 15 Hertz, we see the input signal can almost completely follow the output signal concerning the amplitude. So we have an amplitude gain of 1, but there is a phase lag of 10 degrees at 15 Hertz. At 50 Hertz, we already have an output value of 1/3, sorry. So we have this value here for the gain, which is 1/3, and we get a phase lag of 60 degrees. And we can go through different frequencies. We can measure different frequencies and see the output in amplitude and in phase. Okay, that's good that we can do that, but of course I can imagine that nobody of you wants to take a signal generator, put a certain frequency at the input, measure the output, and not only doing that for one frequency, but for a whole list of frequencies. You need to wait until the system is in steady state with that frequency. You have to measure the phase, which is also time consuming. Sometimes we let our students do that, but in practice you want to go much quicker. And we have a technique, or there is a technique to do it much quicker. Don't put at the input one frequency, but put all possible frequencies that you might need. And then you will also have lots of frequencies at the output. If you apply Fourier analysis, if you apply signal processing on those two signals, you can sort out frequency by frequency what will happen with the gain and what will happen with the phase. You don't have to apply that Fourier analysis or that signal processing yourself. We made a script which enables you to do that without any knowledge, without any background in signal processing. You can just use the script. And we even have a short YouTube movie, a short instructional movie showing you how to use that script. It's quite typical to do such things in MATLAB, but we know that not everyone has a MATLAB license. The freeware version of MATLAB, being Octave, can also handle such issues. So we have the script also in Octave. And we will see today that even some drive software allows you to bypass MATLAB or to bypass Octave, and we can do it immediately inside Starter. So that's quite interesting. And we will also do that today. I said to you, you do not need background in signal processing or in Fourier analysis. That was a little bit exaggerated. There are only two things you need to consider if you do these Bode plot experiments, and that's the maximum frequency and the frequency resolution. If we do an experiment, we will define the measurement time, or the time during which we run our experiment. Moreover, we also define the sample time, the time between two samples of our input signal. And by playing with the measurement time and the sample time, we have a large influence on the actual resulting Bode plot. If, for instance, we take a larger sample time, like you see here, if you take a larger sample time, the maximum frequency will decrease. So the maximum frequency is 1/2 times the sample time. And the frequency resolution, the distance between 2 points in the Bode plot, is 1 over the measurement time. So with the sample time and the measurement time, we define the output plot, the output Bode plot. Let's give some examples. Here we have a Bode plot. We took a certain measurement time, but we played with the sample time. Here we have a sample time of 0.05 seconds, which is quite large. You see that therefore you have a very limited maximum frequency. This is even uninteresting because in our applications, positioning applications, we will have an anti-resonance and a resonance peak. We will need that anti-resonance and that resonance peak. It contains important information. Well, you see here that you don't even see anti-resonance and resonance peak, so something went wrong. So we decrease the sample time to go to higher frequencies. Lower sample time means higher maximum frequencies. And here we start already seeing a good anti-resonance and a resonance. What my colleagues did is even further decreasing the sample time, and you go to very high frequencies. But you see that the last step is not really worthwhile because this information is quite noisy, quite distorted. That's normal, because at high frequencies, your output will not be able to follow anymore. If your output cannot follow, the resulting amplitude of that high frequencies will be very, very low. And a low output value is difficult to distinguish from noise. So it's typical if you have a very low gain, if you have a very low output, then also your Bode characteristic becomes noisy and you cannot trust on it anymore. You cannot use it anymore. We did the same for the measurement time. We started with a short measurement time. Then you see that your Bode characteristic, which is took at a sample time of 1 millisecond, which was the best from the last slide. We select here 1 millisecond as a sample time. Well, we can play with the measurement time, take a very short one, then you don't have a lot of detail in your Bode characteristic. Your measurement time also influences the starting point, the first frequency. This is a very high first frequency, so it's not really trustworthy. You increase the measurement time, you let your experiment run for a longer time, you get more detail in your Bode characteristic, and you start at a lower frequency, which is very valuable. And then you can even increase your measurement time further, and we get even more detailed Bode characteristic. This is all the same system, but all examined with different settings for your sample time and your measurement time, and you clearly see that there is a large influence on the resulting Bode characteristic. It gets much more detailed. We get much more insight in the Bode characteristic. So it's very beneficial to increase your sample time. Unfortunately, in many cases, there is a certain maximum to that, because n is the number of samples times the sample time. In many cases, this number n is limited because the memory of your drive is not infinite. It is a limited memory, and you can also do a limited measurement time, a limited experiment time to measure your Bode characteristic. But fortunately, the maximum measurement time is high enough to have a good result. However, we have a problem right now. Imagine that you have done your first experiment and you see this. How will you be sure that the result is totally untrustworthy? Maybe your colleague says, okay, there is no anti-resonance or resonance, but maybe this is just a system without an anti-resonance and without a resonance, and those systems exist. And you don't know that you have to redo your measurement with a larger measurement. Well, there is one parameter that you get for free, and it's the so-called coherence. In our scripts, you not only get the Bode plot with the amplitude and the phase, you also get the coherence. And the coherence is a value between 1 and 0, where 0 means total rubbish, and 1 means very good quality. So you need to have this coherence as high as possible, as close as 1 as possible. What you see and what you will always see is that for high frequencies with low gains, your coherence is low. That is because the output signals are very limited, so they are not distinguishable from noise anymore. On the other hand, we also see the same effect with the anti-resonance. If you have a certain anti-resonance frequency, your coherence also becomes quite low, and that's also typical because at the anti-resonance point you get quite some the gain is very low, so you get a very low output gain. All right, let's go one step further here. Measurement time 0.5 seconds. Maybe the Bode was okay, but if we saw the coherence, we immediately knew this is not a good measurement. We need to increase the measurement time. If we done this increase, we see much better coherence. Low coherence at high frequencies, typical. Low coherence at anti-resonance, also typical. Low coherence for the first frequencies, also typical, because low frequencies means large periods, and that means the sine wave with that certain period only fitted in your measurement window 1 or 2 or 3 times. And the algorithm actually uses averaging to average out the noise effects, and so you cannot apply that averaging on low frequencies. It's difficult. It's a problem on low frequencies, and therefore you get low coherences here at low frequencies, but luckily at higher frequencies it becomes okay. So this is a good coherence actually. All right, the system identification. I propose for timing issues that I continue. Yeah, I just continue, and we will see where we get and where we can adapt a little bit in the timing, depending on your availability. So what we want to do now is we want to design our controller PI and P based purely on the Bode characteristic of the system. Therefore, we want to separate the system from the rest. We put in noise, high frequency noise at the input. We get a signal at the output. We use those two signals to do the signal analysis and to construct the Bode plot. You can do that in, like I said, MATLAB Octave. We will not do that today because within Starter, within the Siemens software itself, you can already apply this signal processing to identify your Bode characteristic. So why then do we have these scripts in Octave and MATLAB, which we will provide to you, and the video from MATLAB and Octave? We have that because you can also apply these techniques on any system, and it's very probable that if you apply it on a temperature control system or a flow control system, that you don't have a drive or a system which has the capabilities of constructing Bode characteristic, and in that case you need to provide high frequency noise yourself, measure the output, but with the two signals you can put it in our algorithm, you can put it in our script, and you get the Bode characteristic. Very important, if you do this measurement, do it at open loop. Make sure that the PI controller is disabled. You can disable it by opening the loop here or putting the P and the I value at 0, so it plays no role. Otherwise, you will get bad coherences, bad results. You are able to do this yourself in the Drive software. So I will give the opportunity for each and every one of you to do it on our setups. For that purpose, you will need to go to the device trace panel, and there you have the function generator. You need to define the PRBS because you need to put in noise, high frequency noise. Not only that, you also have to play with the bandwidth of that noise. And the bandwidth of that noise is defined by this function, so by the sample time. You put in the good bandwidth there. You also have to put in the good amplitude, that your system is perturbed, is excited enough, but not too much. But you will see in the guide that it helps there. Sometimes it's also a bit trial and error. You get a bad Bode characteristic. You might need to increase the amplitude, so you get higher power in, and your system identification is better. Okay, other You can also turn the reasoning around. If you have a certain bandwidth, you can define the sample time by dividing it 1 divided by 2 times the bandwidth. Then here in that view, you can put in the right sample time by playing with the factor here. So the sample time is always a full an integral amount of times the basic cycle clock. So your controller runs at 0.125 milliseconds. That means that your actual sample time has to be an integral amount of times the basic cycle clock, and then you get here the trace cycle clock. Okay, you can also define the duration, like we said, the measurement time, but here you see always there is a maximum duration based on the limited amount of memory of your system, and you put that in your duration. And then you can do the measurement. I will give the floor again to Santiago, which will help you get started with this hands-on experiment, which you can do yourselves on the setup that is assigned to you, like this, based on this schematic. What you've seen right now is that you're able to measure a Bode plot yourself in the starter software. You can play with the measurement time, like I showed here. You can play with the measurement time. You can play with the sample time. It has a large influence on your Bode characteristic, but once you know that, you can have very good Bode characteristics. You don't need Octave or MATLAB to obtain those Bode characteristics if your drive software permits, back-off drive software permits, Siemens drive software permits, so that's very nice. The disadvantage of this software is that you don't have a coherence, you don't have any number that gives you an idea of how trustworthy your Bode characteristic is. But nevertheless, you get a good Bode characteristic. Once you see a clear resonance frequency, that's also a very good indication that you have a good Bode characteristic. Okay, then let me go through the next slide. Once we have the Bode characteristic, what can we do with it? Well, it can be used for quite a lot. You can use it to identify the stiffness and the damping of your coupling between the load and the motor. But of course, we will use it today in a setting of control engineering.